Are you really doing some software engineering, or are you picking much more complex solutions than you should? Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios, and what I have for you today is a reaction to an article that I saw recently, and it's really interesting because it's about doing the simplest thing that could possibly work. And I believe this is a very sound concept for software engineering, for software design, for design in general, but it applies particularly well for software design and software architecture because they are soft. We can model them, we can modify them easier than, let's say, hardware. If you are to build a bridge, what you can do is during the design process to do the simplest thing that could possibly work up until the point where you actually get to the specifications that you need. But once you build the bridge, you cannot change it that easily. And this is the big difference between software and other domains. And I think the way I put it is the code is the design. The code is really the blueprint that you use in order to build the final product, and the build is mostly an automated step. So it's possible for us to continuously modify and enhance our code, which is really the design, in order to get to the end product that we eventually will need. And I think this article touches on a lot of these topics. So let's go through it and let's see what my comments are. This is an article written by Sean Goedecke, I think. Do the simplest thing that could possibly work. When designing software systems, do the simplest thing that could possibly work. It's surprising how far you can take this piece of advice. I genuinely think you can do this all the time. You can follow this approach for fixing bugs, for maintaining existing systems, and for architecting new ones. A lot of engineers design by trying to think of the ideal system. Something well-factored, near infinitely scalable, elegantly distributed, and so on. I think this is entirely the wrong way to go about software design. Instead, spend the time understanding the current system deeply, then do the simplest thing that could possibly work. So now let me qualify a few of these things, because I believe he's right. I also believe that he's a little bit exaggerating for the goals of this article. So trying to think of the ideal system, something well-factored, near infinitely scalable, elegantly distributed, and so on. First of all, why is this a problem? Well, because in architecture, what you have is a lot of trade-offs. You don't have the perfect system. So if you want to go to near infinite scalability, for example, this will probably increase your operational costs and your operational complexity. And because of that, you move the complexity basically in another place, right? So you're always working with limited resources, limited time, limited knowledge, limited budgets. And so the ideal system is the one that fits within these constraints. And this is the correct way of thinking about software architecture, which means that whenever you design an architecture, you should start from these constraints. And these constraints will include, okay, we need scalability, kind of what level of scalability, and then what are our constraints in terms of money, knowledge, time, etc. So this is, let's say, the way in which I believe we should engineer systems, to use his way of framing this problem. So, on the other hand, you cannot completely ignore the final needs. Now, there's something to be qualified here, because let's say you are a startup and you say you have a user now, and the goal is to have 1 million active users that go into your website every day. I mean, that's a pretty cool goal. Congratulations. But how long will it take you to get there? Just assuming that you can have all the technology you need, how fast can you get there just in terms of business? And my guess is not that fast. There are very few companies who grow that fast. So because of that, it's tempting to think about, what the system will be when we have 1 million users that are active every day. But until we get there, what we have is a bunch of experiments, a bunch of prototypes, a bunch of things that we need to put out so that we validate our product market fit and so on. Which means that you shouldn't think about the final system, but instead just focus on the next goal. On the other hand, if you are more of an established company and you already have a large number of users and you are pretty certain that, 10% of your user base will use a specific product because you will divert them to it, and then you can start from there. And if it happens or if it doesn't happen, it's a business problem. But the job of the technical people is to make sure that they enable the business to go there. So in that situation, I believe that you need to start from the final goal and see how you get there, but at the same time take into account the constraints that you have, and communicate the budget estimates for operational maintenance, for example, cloud costs. Right. So this is what we need to consider in terms of large-scale architecture. Simple can be underwhelming. That is correct. Actually, the best systems I know and the ones that I like the most are the ones that are really boring from a user perspective, because they just work. You don't have to do anything. You start them, they work. You forget about them. They do their thing. They give you the information and notifications and whatever you need. And you don't have to do anything about those. So simple is boring sometimes, but not getting to the simple solution that is not boring, that is actually very interesting. But the final system can be really boring. Let's see what he has to say. System design requires competence with a lot of different tools, app servers, proxies, databases, caches, queues, and so on. As they gain familiarity with these tools, junior engineers naturally want to use them. It's fun to construct systems out of many different components, and it feels very satisfying to draw boxes and arrows on a whiteboard, like you're doing real engineering. However, as with many skills, real mastery often involves learning when to do less, not more. This reminds me of one quote, I think, I'm not sure if it was Einstein, but it's something like, if you want to achieve something simple, then figure out what you need to take out, not what you need to add. And one of my approaches for solutions in software is I clarify the problem, I come up with a solution, ideally with 3 different solutions. But let's say I come up with one, and then I look at it and I say, okay, can we replace parts of it with something that already exists? And the second question is, can we remove some of these features because maybe we don't really need them. They are just nice to have. So these are the two important questions for simplifying. And often you get really good results if you do that, but there's a catch, and the catch is this requires a more general knowledge about the technologies that exist out there. There are many things that are already implemented in Linux, in various application servers and so on. So you need to understand what each part of the system is capable of doing. And sometimes this is where AI is really great. I have conversations with Claude where I start from a problem, I come up with a solution, and then I start asking, okay, but what if we used that? What if we used that instead? And so on. And the good thing about that is that Claude can give me answers that are extracted from the manuals of those tools. And of course, I double check them because never trust AI immediately. But knowing that those things are possible in various tools is extremely useful to simplify infrastructure. However, as with many skill, mastery often involves learning when to do less, not more. The fight between an ambitious novice and an old master is a well-worn cliché in martial arts movies. The novice is a blur of motion, flipping and spinning. The master is mostly still. But somehow the novice's attacks never seem to quite connect, and the master's eventual attack is decisive. In software, this means that great software design looks underwhelming. It doesn't look like anything much is happening at all. You can tell you're in the presence of great software design because you start having thoughts like, oh, I didn't realize the problem was that easy, or oh, nice, you don't actually have to do anything difficult. Unicorn is great software design because it delivers all the most important guarantees in a web server, request isolation, horizontal scaling, crash recovery, by leaning on Unix primitives. So I didn't know about Unicorn, but there's a footnote here saying it's just Unix sockets and forked processes. I love Unicorn. And if you think about it, why not? I mean, this is a very clean, simple solution to web servers. You already have those primitives in Linux, so why not use them? Now, like any tool, it might not fit all the possible problem domains, but you don't have to use it for everything. You just have to use it where it shines. The industry standard Rails REST API is great software design because it gives you exactly what you need for a CRUD app in the most boring way possible. I don't think any of these are impressive software, but they're impressive feats of design because they do the simplest thing that could possibly work. I'm not very familiar with the Rails REST API. I know that Rails is praised. However, personal preference, I tried Ruby and I prefer Python. I like that in Python you have a single way of doing, well, at least that's the philosophy. Try to have a single way of doing one thing. Well, in Rails, there's a lot of syntax sugar and stuff that I didn't quite like. But it doesn't mean it's not a great technology. That's just personal preference. And indeed, I know that it's really great for CRUD apps. So I will give it that. You should do that too. Suppose you've got a Golang application that you want to add some kind of rate limiting to. Don't worry about Golang. It's not only about that, right? So assume you have an application written in whatever language you use, and you need to add some kind of rate limiting. What's the simplest thing that could possibly work? Your first idea might be to add some kind of persistent storage, say Redis, to track per user request counts with a leaky bucket algorithm. That would work. But do you need a whole new piece of infrastructure? Yeah, so whenever you add a new system, and that's similar to what we were discussing before, but it's about scalability, but it's something much more specific. So if I add Redis on top, what I need is, we need to make sure that we install it, we need to make sure that it's started, we need to make sure that it's monitored and it gets restarted, or that we have resilience. We might need to ensure that it stays up, which usually means having 2 instances and so on. And I don't know how much of this is supported by Redis. Maybe some of these features are already in, but I can bet that none of these are free. There's a cost for every one of those. And you anyway need to monitor it, you need to install it, you need to upgrade it, you need to maintain it, you need to configure it. What if you could use something that already exists in your system? Or what if you could do something slightly different or easier, or wouldn't that be simpler? So let's see. But do you need a whole new piece of infrastructure? What if instead you kept those per user request counts in memory? Sure, you lose some rate limiting data when the application is restarted, but does that matter? Actually, are you sure your Edge proxy doesn't support rate limiting already? Could you just write a couple of lines in a config file instead of implementing the feature at all? Yeah, so maybe if you are using, every tech company has some sort of Edge proxy. That was the footnote. So if you are using some kind of proxy, and usually you have it, you have a reverse proxy like Nginx, maybe that, where you need to store your SSL keys and all that. And maybe you can configure it to just work. So why not do that? And this is a very good approach. So it's okay to come up with a solution. The thing that I see not many people do in this industry is to then examine that solution a little bit more and ask, okay, what can we replace? What is already possible in the things that we are using? And so on. So, or what are some things that we can relax in order to get 90% of the result that we want? Maybe your Edge proxy doesn't support rate limiting. Maybe you can't track in memory because you have too many server instances running in parallel, so the tightest rate limit you could enforce that way is too wide. Maybe it's a deal breaker if you ever lose rate limiting data because people are hammering your service that hard. In that case, the simplest thing that could possibly work is adding persistent storage, so you should go and do that. But if you could do one of the easier approaches, wouldn't you want to? I would. Some people just like to build stuff on top of other stuff because it's fun. I can understand that too, different focus. You really can build a whole application from scratch this way. Start with the absolute simplest thing and then only extend it when you have new requirements that force you to. It sounds silly, but it works. Actually, it doesn't sound silly at all. So there's another saying, which is every complex system is the result of a simple system that worked. That's basically it. You start with a very simple system that works and then keep adding to it. Think of it as taking Yang as the ultimate design principle, above single responsibility, above choosing the best tool for the job, and above, quotes, good design. What's wrong with doing the simplest thing? Of course, there are 3 big problems with always doing the simplest thing that could possibly work. Yeah. The first is that by not anticipating future requirements, you end up with an inflexible system or a big ball of mud. The second is that it's not clear what simplest means. So at worst, I'm saying to design well, always do good design. The third is that you ought to be building a system that can scale, no system that just works right now. Let's take those objections in order. Big balls of mud. By the way, we have a whole video on big balls of mud because it's one of the patterns that holds for many, many years. And check that out. The paper is incredible. You can also read the paper if you prefer that. Because yeah, there's actually a paper. Big ball of mud is a design pattern. Maybe not one that you'd expect, but it's kind of de facto default architectural pattern out there. To some engineers, do the simplest thing that could possibly work sounds like I'm telling them to stop doing engineering. If the simplest thing is usually a quick clutch, does that mean this advice will inevitably lead to a complete mess? We've all seen code bases with hacks stacked on top of hacks, and they definitely don't look like good design. But are hacks simple? I actually don't think so. The problem with a hack or a clutch is precisely that it isn't simple, that it adds complexity to the code base by introducing another thing you have to always remember. Yeah, so I guess that's a problem with understanding what complex means and what simple means. One issue is that sometimes simplicity is confused with familiarity. And it's not always the case. Like, let's say you want to process collections. The simple code that everyone knows is, or the familiar code that everyone knows is to use for loops and go through the collections and repeat that code again and again and again and do all the processing you need. The less familiar ways to use functional programming techniques and higher level functions to process these collections. It wasn't as familiar, and I'm pretty sure it still isn't as familiar for programmers, but it is simpler because there are fewer things you need to pay attention to, and you get better. The intent is better represented in the code by using the functional constructs. Because when you see a for loop, you need to actually read inside the loop to figure out what kind of loop it is. What are you trying to do? Are you trying to modify the collection? Are you trying to enhance it? Are you trying to turn into something else? Are you trying to remove things from it? What are you trying to find things in it? Whereas with the functional higher level functions, you know precisely what it's doing because it's in the name. You're trying to, if it's find, you're trying to find things. If it's map, you're trying to transform a collection into another collection, and so on. And this is one of the examples. And adding another thing is that if you don't understand the code anymore because it has too many things on top of one another, then that is not simple enough. You can probably make it simpler. And one possible way to do that is to divide and conquer, so split into smaller pieces. So these are a few general ideas for surprising simplicity, let's say. Hacks are just easier to think of. Figuring out the proper fix is hard because it requires having to understand the entire code base or large sections of it. In fact, the proper fix is almost always much simpler than the hack. Yeah. It is not easy to do the simplest thing that could possibly work. When you're looking at a problem, the first few solutions that come to mind are unlikely to be the simplest ones. Figuring out the simplest solution requires considering many different approaches. In other words, it requires doing engineering. Yeah, I completely agree. What is simplicity? Now this is interesting. Engineers disagree a lot about what constitutes simple code. If simplest already means with good design, is it just a tautology to say it should do the simplest thing that could possibly work? In other words, is Unicorn really simpler than Puma? which is apparently another web server. Is adding in-memory rate limiting really simpler than using Redis? Here's a rough and intuitive definition of simplicity. Number one, simple systems have fewer moving pieces, fewer things you have to think about when you're working with them. Number two, simple systems are less internally connected. They are composed from components with clear, straightforward interfaces. Unix processes are simpler than threads because processes are less connected. They do not share memory. This makes a lot of sense to me, but I don't think it gives you the tool to figure out what's simpler in every case. And I guess that's the big problem, the big challenge, because while this rough definition is correct, it's not complete. I would also add maybe that in a simple system you use the most of the tools that you have rather than trying to reinvent the wheel. And there are probably other things that we might add. What do you think is simple? Now I'm curious if you can add in the comments what you think other criteria for simplicity are. What about in-memory rate limiting versus Redis? On the one hand, in-memory is simpler because you don't have to think about all the things involved in standing up a separate service with persistent memory. On the other hand, Redis is simpler because the rate limiting guarantees it offers are more straightforward. You don't have to worry about the case where one server instance thinks a user is rate limited and another one doesn't. When I'm not sure what seems simpler to me, I like to use this tiebreaker. Simple systems are stable. That's a good one. If you are comparing two states of a software system and one will require more ongoing work if no requirements change, the other one is simpler. Redis must be exactly what I was saying. Deployed and maintained, it can have its own incidents, it requires its own monitoring, it requires separate deployment in any new environments the service finds itself in, and so on. Thus, in-memory rate limiting is simpler than Redis. Yeah, so very interesting. And the third one, why wouldn't you want to be scalable? I think we touched on that, but let's see. A certain type of engineering is now screaming to themselves, but in-memory rate limiting one scale, doing the simplest thing that could possibly work, will emphatically not deliver the most web-scale system. It will deliver a system that works well at the current scale. Is this irresponsible engineering? No, I don't think so. I mean, you should look a little bit ahead, but let's say you already have a system and you need to implement this. You should have an idea by now how many requests you expect, even if you're growing, like how many more requests per minute you would expect. So based on that, you can make the decision. But I believe that usually what happens is that you go to a point, up to a point where you can go without the separate piece of technology, and then you need to switch because that's what happens. But it's very rarely that this growth is exponential. Usually, even if it's fast growth, it's only exponential up to a point and then it slows down. So no, in my view, the cardinal sin of big tech SaaS engineering is an obsession with scale. I've seen so much unavoidable pain caused by over-engineering systems to prepare for several orders of magnitude more than the current scale. Yeah, I mean, you probably can expect reasonably, let's say, 10 times more requests in the next year, but then you revisit. Now, of course, there are different types of systems. So for some of them, it's not like that. They will grow much faster. But more than 10, maybe let's say maybe 100. But more than that, it's And if you get to that point, you probably need to change much more in the technology than just this particular decision. The main reason to not try this is that it doesn't work. In my experience, for any non-trivial code base, you can't anticipate how it will behave at several orders of magnitude more traffic, because you don't know ahead of time where all the bottlenecks are going to be. That's what I was trying to say. So even if you focus on optimizing perfectly this one thing in your system, if you grow 10,000 times more, it's likely then the system will blow up somewhere else. So you need to figure out the bottlenecks. And if you are serious about that, the only way I know is to run simulations and figure out where things are going wrong. But there's a trade-off, because those simulations are expensive. You need to deploy those instances, you need to make calls with even simulated calls that are much, much larger, and then figure out what the bottlenecks are. And is it worth it doing that? Probably not for every system. For some systems, it might be worth it. If it's life critical, if it's maybe business critical, maybe in those cases, yes. But for a management style application, I don't think so. At most, you can try to make sure you're ready for 2 times or 5 times the current traffic, and then stand by to deal with problems as they come in. Yeah. So it seems that he disagrees with me. I said 10 times. But yeah, different experiences, I guess. The other reason not to try this is that it makes your code base inflexible. Yeah, it's fun to decouple your service into 2 pieces so they can be scaled independently. I have seen this happen maybe 10 times, and I have seen them actually be useful scaled independently maybe once. 1 in 10. But that makes certain features very hard to implement, because they now require coordination of the wire. In the worst case, they require transactions over the wire. Oh boy. Which is a generally hard engineering problem. Most of the time, you just don't have to do any of this. Yeah. So if you're going into the area of distributed transactions, you start to get a lot of pain. Avoid those. And, well, I am teaching a course on architecting microservices where we talk about how to solve this problem, but the solution is not that easy. So the ideal way is still to try as much as possible to avoid distributed transactions. And if this means that part of your system is not microservices, that's the better architecture, probably, or at least the simplest, which, as we've seen, is probably the better one. Final thoughts. The longer I spend working in tech, the less optimistic I become about our collective ability to predict where a system is going. That's true. Don't try to predict. There are some general lines that I keep talking about. One of them is one will become more. So if you have one item in, let me put it this way, if your product owner tells you that you will only support one currency in your system forever, you can be very sure that at some point you'll need to support a second currency. The second law that I see with evolving requirements and software is a constant will become a variable, will become a function. So let's say you have maybe a discount, right? and you say everything is 5% discount. We don't give any other types of discounts than 5%. And then later on, you can be definitely sure that somebody will come and say, oh, I need 5% for that, 10% for that. Your constant has just turned into a variable. And then they will come up and say, okay, so if the visitor, let's say, has in the shop cart 3 items of one kind, then we also need to give it 15% discount on something else. And that's a formula. These are kind of the lines we can expect software to evolve, and some of them will be more likely than others. But actually predicting what will happen, that's generally not a good idea. It's hard enough to get your head around where a system currently is, and in fact that's the main practical difficulty in doing good design, getting an accurate big picture understanding of the system. Most design is done without that understanding, and most design is thus pretty bad. There are, broadly speaking, 2 ways to develop software. The first is to predict what your requirements might look like 6 months or a year from now, and then design the best system for the purpose. The second is to design the best system for what your system actually looks right now. In other words, to do the simplest thing that could possibly work. Well, and here is the rub. In many corporate environments where I've been involved, they get requirements that are very large, and they say, this is the product that we need to have for our users, blah, 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 blah. It's been analyzed, market analysis, whatever. We have all these numbers that statistics that show, and the CEO has said that this is important, and so on. And you get a huge set of requirements, and then you look at those and you try to match the expectations. Guess what happens? Either the product is very delayed, so then you need to descope, which means you basically cut down features and things that you prepared for the final ideal vision actually are not needed. The product might not get that much traction in the marketplace as expected, because every analysis is really a guess. So, or maybe there was a competitor that came out of nowhere and provided the same service before you. And then what do? You rework the features and you figure out which is a better product market fit, or you decide to kill the project, and so on. So in all these situations, it's very rare that you actually get a set of requirements, you implement those exactly, they get deployed, the users are happy, everybody gets on board, and everything goes according to plan. Rarely, if ever, happens. So most of the times, making the simplest thing that could possibly work is the better strategy. And I say most of the times because sometimes you need a minimum set of features in order to match other products. And in those cases, well, you need to start there. It depends a lot on your market. But you have to know what business you are in, right? That's one of the first things for architecture. This article has gotten some comments on Hacker News. One interesting comment thread says the simplicity of architecture doesn't matter at scale because the complexity of state space exploration in implementation dominates any other complexity. I disagree. The more complex your feature interactions become, the more important simpler architecture becomes because your complexity budgets is almost exhaustive. I also want to credit Ware Cunningham and Ken Beck for inventing the expression. I genuinely thought I'd just come up with the wording myself, but I most certainly just remembered it. Thanks to the HN user ternary operator for pointing this out. Yeah. I didn't imagine that he... Okay, so he actually believed he invented it. Yeah, it's Ware Cunningham and Ken Beck. Like almost every cool technique from the past 40 years, it's probably Ware Cunningham somewhere. Okay, so I completely agree with all this, and I already gave you a few ideas on how to do it. Whenever you get a problem, try to state clearly the problem and then come up with a solution, but then critique the solution and try to figure out, could this part of the solution be made simpler by using existing things, or maybe by just expanding one small part of your system. So let me give you an example. Just today I was evaluating one thing, but it will take a few minutes to explain. So I decided to use for my personal planning a single markdown file. And in that markdown file, I have as headers, I have my areas, and then I can have subheaders where I have projects, and then I have bullet lists with the tasks, which are sometimes are tasks, but other times are really increments, so things that I need to add on top of existing things. And it's working really well. Once again, it is the simplest solution that would possibly work. There's something similar called to-do.txt created by Gina Trapani, but I like Markdown better because I can I'm actually using this in Obsidian, so I can link with other nodes, I can format things better, and so on. So that's fundamental idea. And then how do you mark a task done? Well, we have the option to have a line through, right, in Markdown. So that's how I format that with the line through, is 2 tildes in front, 2 tildes at the end, and they show this line. So it's pretty easy. But one thing that I wanted is to add some kind of coloring, some kind of styling on dates. But I like that to be automatic as much as possible. I can style dates, but I find it a bit cumbersome. So I was thinking about solutions. And what would be the first solution? The first solution would be to have a CSS style that applies to a template, but there isn't such thing. So you cannot apply to a style based on a regular expression. Another thing would be to create an Obsidian plugin, which could take the whole file, process it, and then add the right coloring and so on. A bit cumbersome. But then what would be really cool is if I could get into the process of creating. So Markdown is processed, and in that process is turned, let's say, into HTML. And I could get into that process, plug into specific regular expressions when they match, and only then add a kind of a span with the correct style. Now, even more interesting, maybe we could add some special HTML attributes that are used by the CSS style in order to do that. So then nothing changes. And let's say you format the date with an @ in front, and it shows the date. And you just have a small thing that matches, that basically creates the span with the right class or the correct attribute, and then you apply the class on the custom attribute. And I'm still not fully happy with this. I'm thinking about even simpler solutions, but that's kind of like my thinking process. Because it would be easy to create an Obsidian plugin, but then you have to maintain it. It will have bugs. There's more chance of bugs. But if you could plug into the Markdown generation, the Markdown, I don't even know how it's called, but it has Markdown, at least Pandoc has filters that can be used in Markdown, and you could add a filter that does part of it. And so every piece of technology will kind of fit. And the nice thing about that is that they can work independently. Whether it's in Obsidian, whether it's outside, and you're using Pandoc, it will kind of be a standard. So that's what I'm exploring. Now, if something like this exists, I will definitely use something like that instead of me writing my own thing. But it would have to be just very pointed, just introduce dates or formatted dates, and that's it. Right? So this is one example of doing the simplest thing that can possibly work. And my fear is that too often developers jump on the first solution, on the most familiar solution, and they just go with that one instead of considering alternative options, which would result in much simpler designs. So what do you think about all this? What are your thoughts? What are your experiences with simple architecture, simple design? Are there cases when you cannot do that? Do you know other techniques? Let us know in the comments. We love having conversations with you, so yeah, write down a comment. It's always well received, or at least say hi. Hi is good. Thank you kindly for the view, and until next time, remember to think, design, and work smart. See you next Saturday.